Thank you everyone for attending today's webinar, Advanced Modeling and Simulation Techniques for Multibody Robotic Systems, brought to you by Design World Magazine. We want to thank our presenters for being here today and their respective organizations, Maplesoft, AEMK Systems, and the University of Waterloo. I'm Laura Carabine, Senior Editor, and I'll be your moderator today. Just a couple housekeeping details before we get started. If you wish to tweet about this webinar anytime during or after, you can use the hashtag DWWebinar. We will have a Q&A session after the presentations. Go ahead and submit your questions, and we will ask them after the presenters are finished. Questions can be posted using the GoToWebinar on your screen. First, we will hear from Paul Goossens, Vice President of Application Engineering at Maplesoft. He is a mechanical engineer with more than 20 years of experience in engineering and software business management. Then we'll hear from Dr. Amir Khajapour, President of AEMK Systems and Professor of Mechanical and Mechatronic Engineering at the University of Waterloo. He's an authority in mechatronics and robotics. His research includes modeling and development of advanced systems for the automotive, space, and manufacturing industries. Presenters will be available to answer questions after the presentation. Now, without further ado, I'm handing the mic over to Paul.
Many thanks, Laura. Welcome, everybody. So we're going to spend a little time today talking about modeling and simulation techniques that are based around tools that have been developed at Maplesoft. And this includes a product called MapleSim. Just advance my slide here. So I'm just going to set the scene in terms of what's driving Maplesoft to be developing model-based design tools for this particular application area. So that should take me just a few minutes, and then I'll pass the microphone over to Dr. Khajapour to actually take a look at some case studies in some detail. And then I'll just wrap up by a little description of the products that have been presented during Dr. Khajapour's session. And then we can open the microphones for Q&A. So to set the scene and what's really being motivating the development of the tools at Maplesoft has been this whole move towards developing virtual prototypes of complex mechanical multi-domain systems in order to ensure that the design of the system is going to behave in the way that you would expect it to behave. This really helps to reduce prototyping costs, so you can actually get a good assessment of how the system is going to behave within simulation before investing in building a prototype, which would be typically where you would find a lot of the design flaws, and you can iron out a lot of those flaws during that time. This opens up the way for adding more functionality into your products, and also makes the products more reliable. And of course, this is critical in many robotic systems, and certainly some of the systems that Dr. Khajapour was going to talk about is when you're actually sending a system out to space, and you need to be able to come up with a good way of being able to perform extensive tests on the system and on the ground, and make sure that the system is going to do what you want it to do. So part of that process is becoming increasingly required to be able to test virtual subsystems through hardware-in-the-loop types of applications. And this could be for the validation of subcomponents with their controllers, and just making sure that those parts of the system work well before integrating into the rest of the vehicle, or to take a look at the whole system and ensure that all those subsystems are interacting with each other correctly, thus reducing development cycles, and certainly when you're developing a product, time to market is a major factor. So this greater demand for virtual prototyping has also meant that there's a greater demand for model fidelity, to add further details into your real-time models. And this has raised a few challenges that we think we are addressing in the tools that we provide. The first one is just scalability. So as people are adding more and more complexity into their models, the actual computation platforms are becoming quite restricted. There was a time when Moore's law basically meant that if you waited 18 months, then you would have a doubling of clock speed. That should alleviate that issue. But of course, that's not happening now. So we're starting to see approaching the threshold in terms of what kinds of systems can be actually modeled and simulated in a real-time context in particular. Oops. There's also the notion of being able to combine various different engineering disciplines into one environment using multi-domain modeling tools. And traditionally, the way you would do that would be to use some kind of signal flow modeling tool, for example, Simulink, to provide a way of having inputs going into a subsystem, something happening within that subsystem, and then the results of that being passed out as an output into the next system, and so forth. Which is all well and good until, for example, you want to apply a load at one end. Now you have to explicitly account for those loads in your system, which means you have to completely reformulate the system model, which again adds more burden to the model development process. And then the final challenge is just the ability to incorporate a lot of detail in your model. Typically what happens is when you want to achieve real-time performance, you have to strip away a lot of the detail to a point where you have a much simplified model, which doesn't truly reflect what the original mechanism is supposed to do, and that really reduces the usefulness of the real-time testing in the first place. So these are the kind of challenges that we've been helping to alleviate with our tools, and I'll talk a little bit more about that in detail at the end. So what I'm going to do now is just to pass the microphone over to Dr. Hashpour, who will take you through some of these case studies using our tools.
Thank you, Paul, and hello, everyone. I'm going to talk about 3 of my recent projects that are related to space applications, planetary rovers, automotive pulse active steering, and robotics application in cable-based parallel robots that we have used Maplesoft both for modeling and optimization, and in 2 of these projects also for hardware in loop analysis. So I'm going to start with the first application, which was for rover design. And that was a project that we had with Canadian Space Agency and Maplesoft. And the purpose of this project was to establish a design platform that we can use for modeling, simulation, and animation of rovers, and at the same time be able to do hardware in the loop analysis. So when we look at a rover has, any rover has some standard components like wheels, solar cells, wheel motors, battery, power electronics, heaters, and robotic arms and accessories. And when we put that onto any train, then we have to be able to model the train, environment, and also be able to do simulation and animation. So what we did, we used Maplesoft, and for that one, we started developing some custom-made components, and at the same time using the built-in components that Maplesoft has in the software. So what you see here is the overall model of the rover, and the picture of that rover that is also in Maplesoft is shown on the top right of this picture. Now I'm going to go through this a little bit just to see how you can relate the components of the rover to the model that we have. On the top part of this model, we have the body of the rover that we have University of Waterloo printed on it, and that is the main body which has the mass, and also 2 revolute joints on the side. These 2 revolute joints are on this one, and the other one is on the other side of the body. Remember that this is for a 6-wheeled rocker bogie rover, and obviously we can use the same approach to design or model any other type of rovers. Now, the design of this is based on a differential mechanism that it sits right inside the body, which means that between these 2 revolute joints there is an algebraic equation, algebraic constraints. And that is done by this block that is shown here on top of the model. Now, if we follow this, then the revolute joint here is connected to an arm, the blue arm that you can see on the picture. And through that arm, we have 2 revolute joints. One revolute joint that is connected directly to one of the wheels, which is this wheel in the picture. And then the other revolute joint that you see here that is connected to the yellow arm that you can see again in this picture. Now, the yellow arm is connected to one wheel on the top, and that wheel is an idle wheel. And through, again, another revolute joint that you see here is connected to the 3rd wheel on the right-hand side of the rover. Now, when we look at, again, this design, it's very similar to the actual, to physical look of the rover. Now, in order to add the other components, like the control of the steering system or the drive of this rover, then we have connected this revolute joint, which is in the front one, and this revolute joint, which is the one in the back. These 2 are connected to the steering block here. That steering block is controlled by the input that you see from the left-hand side of the model. The other component that we obviously need to add is to be able to drive the car, the rover. And that is based on assuming that the front and the back wheel of the rover are the driving wheels. And these 2 are connected to the other input from the bottom side, and we are assuming that we have a position or velocity driver in this case. Now, this block is going to be is a representation and a model of whole rover. And if we go to the next slide, then you can see that on the left-hand side we have a library of all components that can be used for this rover, or it can be used for other rovers. And as an example, you can see here that the wheel and the tire and its interaction with the train is modeled specifically, and that now is a tailor-made component that can be added to this library. So again, the animation and the movie is showing exactly the rover that we had in the first slide on the of the rover, and also the train that we have developed using the information that could be available from the scanning of, let's say, Mars or moon surface. So that can be added very easily into the model. And then to go through again a little bit about the other components, one of the components that we obviously had to model was the amount of energy that the solar panels can get from the sunlight. And in order to do that, we have to look at how we can model the relative orientation of the solar panels depends on the rover position and orientation with respect to the sunlight. And in this model, you can see that how we are looking at the radiation on Mars by looking at all the information on the left-hand side of the model, like vehicle tilt and other information that we have here, and then use that information in order to generate exactly the orientation of the panel with respect to the sunlight. And then using that information that is a separate block, then we should be able to add or send that into the model of a solar cell. Now, on the top left side, you can see the physical model of a solar cell, and then on the right-hand side, you can see the electrical model of that cell. Now, in the bottom part, that is the Maple model, which looks like almost identical to the electrical component. And again, remember that all these elements that you see here are all standard components in Maplesoft. from the left-hand side, we are taking the information of the irradiation from the previous model. We also feed the temperature, and then we use this block that is the constitutive equation of the solar cell, and then that is generating current. That current is in fact that source of current that you can see in this electrical model of the solar panel. And then from there, the rest of it is in fact exactly similar to what you see in the electrical model. We obviously have added some sensors in order to measure the current, the voltage, and also down here you can see how we have used the current and voltage in order to calculate, for example, the power. The next step that we did here was to connect this to a real-time simulation and hardware-in-the-loop environment. In Maplesoft, there is a connector or a component that you can compile or pass the blocks to LabVIEW. So it has a connector for LabVIEW, so you use exactly the model that you saw in the previous slides, and using this connector, you can pass them or generate a block that can be read in LabVIEW. Now, this is a LabVIEW model. However, the boxes shown in blue, this one and also the other one on the left-hand side, are those blocks that are used for, that have been generated through Maplesoft. And by putting those into this diagram in LabVIEW and adding all other components, then we should be able to do real-time or hardware-in-the-loop simulation. Now, this diagram is showing exactly what we have done in terms of the overall structure of this HIL system. On the left-hand side, on the input box, we have all the information related to the rovers, like the path planning optimization that is coming from another program, rover kinematics, and anything else that is related to the vehicle. We have used Maplesoft in order to model or take all the information into that model, and then we have used the connector module in Maplesoft in order to generate a LabVIEW component. And then from there, we have used the NIPXI from National Instruments for real-time simulation. Now, the information obviously are passed or can be replaced from the computer model or using the actual hardware model. So if you look at on the right-hand side block, we have all these components that we have, again, in our lab for hardware-in-the-loop analysis, like halogen lamps, solar panels, and charge controller, battery, and other things. And the beauty of this was, if we wanted only to check the solar panels and the halogen lamps, we only took those two as the hardware components, and then the rest of these were inside the software or inside the LabVIEW environment. And for the whole system, we could still use exactly the same thing. However, the controller was still sitting inside LabVIEW. And using the advantages of Maplesoft in terms of modeling and the very good graphical user interface of LabVIEW, then we can have a very nice environment for any type of testing. This one shows a screenshot of the GUI that we developed for this one, and it shows all the graphs that are related, for example, to the rover environment, solar panel, or the battery, and also the parameters that you can change on fly. Some of the parameters that you can change on fly and see the effect of those parameters on the overall system. So that was the first project that I just reviewed that one. The other project that we recently used and did using Maplesoft was related to active steering system. It's a new method we have developed here at the school, and that is pulse active steering system. Now, with active steering, what we do is to change the input of the driver by adding or subtracting some angles from the input of the driver in order to have a better control, better yaw control of a vehicle. Now, what we have done was to, instead of changing that continuously, we are using a pulsation to the steering angle, similar to ABS. And we have shown that that increases the overall stability of the vehicle. It will become less sensitive to the road conditions, and also in terms of the implementation is going to be much easier. So if you look at this diagram as the overall picture of a vehicle, then on the front side of this we have the steering angle. Let's call that delta, which is the input from the driver. And then we have a controller that is looking at the vehicle dynamics, or the yaw of the vehicle and the yaw that the vehicle should have at that time. And based on the difference between these two, the controller may activate that pulsation. Again, similar to ABS, that if the wheel is getting locked, then it releases the pressure, or vice versa. So by adding that pulsation, then we can, in average, increase the overall input of the driver, or if the pulsation is in the other direction, then we can reduce or subtract from the input of the driver. So what we did, we use again Maplesim and all the standard components that we have in Maplesim in order to come up with the overall model of the vehicle. So I'm going through this just a little bit to see how that the vehicle model is established here. This section that you see here, the center part is the mass of the vehicle, and then these four are the corners of the vehicle, and those are the suspension. And then the suspension in the rear part of the vehicle are connected to a wheel through these two revolute joints. And then from the front, it's connected through these two revolute joints again that are indicating the steering system, and this one and this revolute joint for the rotation of the wheels. And then we have added the controller, the inputs for the steering motion, and also another input from bottom and the top for the torque going to the front or the rear wheels of the vehicle. So that's the overall model of the vehicle. And then the next thing that we did was to convert that into a Symbolic model, because the hardware in the loop system that we use here was MATLAB real-time workshop. So what we did, we developed the model of the vehicle in Maplesim. We converted that into an S function for Simulink. We exported that into Simulink, and then around that we put as controller and also input, hardware input and output. So if you look at on the left-hand side of the diagram, you see the analog input, encoder input. So these are coming from the actual hardware that we have. And then the hardware that we had for this system was a driver steering input that, again, one of the students was trying this. And then we had one electric motor that was used to generate that pulsation, although in practice we do not need that electric motor, but that was the easiest way to add that pulsation. And then we have another motor in the back that is showing the realignment torque that is coming from the wheels back to the driver steering wheel. The rest of the system, which is the dynamics of the vehicle, is sitting inside the computer, and it's run and is simulated to generate, again, the pulsation if it's necessary and the realignment torque. Now, to add a little bit of virtual reality to this, that the driver can see exactly where she or he is driving the car, we added that virtual reality and a road, and we asked them, the driver, to try to stay on the road. And then we activated or disactivate the controller and see the effect or the performance of the overall controller. So that's a animation that is showing how the car will perform when we have the controller and when we deactivate the controller. The last topic that I'm going to discuss here is a new series of cable robots that we have developed again at the school, and we are commercializing those robots at AEMK Systems. And that is based on parallel robots, but instead of using rigid arm, we have used cables. Now, for those of you who are familiar with parallel robots, they have lower moving inertia compared to serial robots. And because of this, you can run them at much higher speed. Now, in order to reduce even the inertia even more, what we have done is to replace those rigid components, rigid arms that are carbon fiber to cables. And in order to keep those cables in tension, we have added one passive cylinder, pneumatic passive cylinder right in the middle in order to keep all these cables in tension. Now, one benefit of this, as I said, is reducing the inertia. The other advantages are reducing the overall cost of this robot, because instead of using carbon fiber, we use cables, which are much, much cheaper. And the second one is to eliminate the load capacity that we have in conventional parallel robots. With this robot, we can run it at high speed with low mass, and also at high capacity, 20 kilograms at low speed without any problem. Now, one difficulty in the design of these robots is to understand and optimize the overall system, because there are many, many factors here. This robot on the right-hand side is a 3-axis XYZ plus a rotational angle right at the end effector. And the other one on the left-hand side is providing X and Z motion plus a rotational motion that is coming directly from that central cylinder. Now, as I said, the question is, what would be the optimum design of this, considering that by changing the length of the arm, we may have larger torque, for example, at the motors, or, for example, in this case, when we add mass to the end effector and move it at different speed, then we have to make sure that the cables are not going to be a slack, because that's another type of singularity that could happen in cable robots. So in order to optimize the design, we need to have a very accurate model of the system. And also for the optimization, it's important to have all the equations in order to do some sensitivity analysis and faster optimization. So I'm going to take you through some modeling aspects of this and see how we have modeled this cable robot. Now, we are focusing on the 2-axis robot. In the bottom, that's the final design that we fabricated from this solid model. And on the top, that's the model visualization model from Maplesoft. And then on the right-hand side, that's the final model that I'm going to talk a little bit about how we have developed that one. So if you look at the left-hand picture, we have some fixed points. And those fixed points that, again, we have revolute joint, but those revolute joints are connected to the ground. In order to generate the ground frame, then it's very easy, because we can bring in that fixed frame from Maple library and drop it into the workspace, and then give all the information related to that fixed frame with respect to the global frame that Maplesoft is using. The next step, obviously, is to be able to make a link, and the link that is connected to that revolute joint. And again, for that one, Maplesoft allows you to bring in, again, mass, rigid body, and then after that you can bring in a rigid body frame, which is in fact links. So it generates the this point, the one. So what you see here, that's the mass of the link. These 2 points, that point and this point on the right-hand side, are the start and the end of the arm. And again, the other 2 that you see here, these are rigid body frame or links that are showing the end points of this arm. So it's very easy to make this. Now, the red symbols that you see here in this model are in fact the CAD model that you can attach to your model, to your Maplesoft model, in order to have a better visualization of what you are making.
So we have the ground frames, 3 of them, and then these frames are connected to 3 revolute joints and connected to the arms that we saw in the previous slides. In this case, we have collapsed them into one single box in order to eliminate any clutter in our model. Now these revolute joints are in fact the revolute joints that you see in this picture, and the revolute joints are connected to those arms. The next step is to make the triangle that we saw in the original design that are connected to the first two arms, this arm, this triangle arm. In order to make this, we follow the same method that we discussed for the design of the arm. So you see in this figure that we have two masses for these two arms, and then we have revolute joints, and these red items are just showing the look of those arms. And then we have rigid body frame, and the rigid body frame are those that are showing the connection between the triangle frame to the revolute joints and then to the other arms. The most difficult part of this modeling is the cables, the models of the cables. To model the cables, we know that cables can only handle tensile forces, not compressive forces. In order to do this, we are going to use a prismatic joint, and then that prismatic joint, now we are going to connect it to two masses. These two masses are in fact the masses of the rod ends at the end of the cables, and also if we want to consider the mass of the cable. Now for the prismatic joint, we can consider stiffness, we can consider damping, and that way what we can do is to change the stiffness of the cable.
In order to add that stiffness property, MapleSim has a template in order to generate any form of stiffness. And if you look at the cable, a cable has, again, an ideal cable, has a fixed stiffness when it's on the tension, which in this case, that is the red line that you see here. And whenever the cable goes into a compression, then the stiffness will go to 0. So if we assume that that's the type of stiffness that we want for this ideal cable, then we can generate that using the MapleSim template for adding stiffness, and then input that as the stiffness for our prismatic joint in the previous slide. And then based on that, we can have a cable model. So again, continuing with that, then you see that now we have the main three revolute joint that you see here. These three main revolute joints connected to the ground. So these are actually these three revolute joints. And then these three revolute joints are connected to three arms. These are the arms. And then the arm on the top, you see that is connected to the cable set. Now each arm has two cables. So what you see here, this link here, in fact, that is two cables that you can see is connected to this cable set. And the cable set is made of the cable model that we discussed, plus two universal joints at both ends. So that will be this link, and the other one is connected again through two, this is again the arm, this is the other arm, and then through these two revolute joints are connected to that arm triangle that we just discussed. And then that is connected through two cables to another cable set, and the other one, other link that we have here, the other link that we have here is connected to the end effector through another two cables to the end effector. Now the only piece that is missing from the overall model of this cable robot is the end effector. And the end effector is also simple to design because the end effector is in fact a rigid component. So we have considered the mass of the rigid component, and then we have added again links in order to identify and locate the location that the cables are going to be connected to, and then we have turned that into a block that can be connected directly to the cable sets that you saw before. So these lines that you see here are the lines that are connecting the end effector to the cable set through those universal joints that you saw before. So at the end, we have the overall model of the cable robot, 2-degree cable robot, and then the next step is obviously to add the cylinder. And for the cylinder, the design will be as simple as the other components that we discussed. So we start with another rigid or the frame, fixed frame, and then we add another revolute joint, and that revolute joint is in fact right on the top here. And then we add the cylinder body and the cylinder piston through a prismatic joint here. And then after that, we add another revolute joint, and that revolute joint is in fact right on the end effector right at this point. So by adding the cylinder, then we have all the components related to the construction of the robot. And the next step that we need to do is to add the control drive for the motors, the two motors that are used to drive the robot, and you see those two right on the top. These again on the top, that's the standard block in Maplesoft, and on the left-hand side, that's the input that you can generate, or if you have any lookup table or something, you can also include that into that input signal. So we have two motors, right, one on the top and one for the other arm that you see here. And in the bottom, we also are adding the applied spine force for that cylinder. Now remember that the cylinder is a pneumatic cylinder, and we are assuming, or we have considered here, that the pressure of that is fixed. Even if you assume that the cylinder goes into the air, goes into compression and expansion, then you can add any form of equation that you have for the model of the air, and then include that into this model. And then as you see, we have added, for example, torque sensors to measure the amount of torque that the arms are handling. That is very important for the motor selection. And also at the end, you see that symbol in order to trace the end effector motion. Now, that is the full model of the system. And then what, again, Maple allows us is to be able to simulate this, and at the same time, since it gives us all the equations, then we can use the equations to optimize the overall system. Again, as I said, there are many factors here, like the length of the arm, the length of the cable, and the distance between the cables and the end effector. And the question is, what is the best combination of the geometrical and also the motor selection in order to have a robot that can meet all the specifications that you have. Again, as I said, the most important thing here is considering that the cables can only handle tensile forces. And if they go into a slack mode, that means that the overall robot is going to lose its rigidity. Now, I'm going to show you some of, again, those simulation results and showing you in what cases we are going to see slack cables. So the red lines that you see here, that's the forces in one of the cable, and this one is the force in the other cable. Now, as you see, both of these two cables going into negative tensile forces, which is a compressive force, which means that the cables are going to be a slack. Now, the blue lines are showing the torque that goes into the motors. And again, as you see, the torque is mostly positive except for a short period of time here. Now, having negative torque, there is nothing wrong with that. What is, again, important here is not to have any negative force in the cables. Now, how we can deal with this, we have shown, again, theoretically, that this system, by increasing the pneumatic force, the pneumatic cylinder pressure, then we can eliminate any compressive force in the cable. And as you see in the next slide, we have increased the pressure inside the cylinder, and now we do not have any negative or any compressive force in the cables. And obviously, the torque in the motors have increased. And that is exactly the trade-off that I mentioned, because you design the robot for a set of specifications. And at the same time, you are not you do not have access to any motors with any torque and speed specification. So if you are targeting a supplier, then there is a list of motors and gearboxes that you can use. And now which one could do the job for you to meet all the specification, and how you can come up with all the dimensional or the geometry of the robot. So what we did, we used all the equations, we put them into an optimization, and also considered the existing off-the-shelf components from a supplier, and based on that, we optimized the overall design of the robot. So I'm going to pass the mic to Paul. Thank you.
Many thanks, Amir. So I'm just going to quickly wrap up, and then we'll open the floor for questions. So just to give you a sense of what the tool Amir was talking about is this is MapleSim. It's a multi-domain modeling and simulation tool that is based on some unique aspects that we are able to bring to the table using our symbolic computation technology, which is what Maplesoft has been well known for in terms of being able to handle equations and simplifying equations and so forth. This allows us to be able to take very complex systems and extract the equations and simplify systems down to their core set of equations of motion. We provide multi-domain palettes of components, so this includes electrical, mechanical, thermal, hydraulics, and so forth. It's particularly designed for the plant model to develop in a controlled design context to be able to produce the system that you wish to control, or a model of the system that you wish to control, and this can be very complex. We're using the power of Maple to do to allow you to do extensive analysis of the model. So the Maple is tightly integrated with MapleSim to allow you to take the model, bring it into Maple, visualize the equations if you wish to do so, extract the equations. These are fully parametric, and you can use this for doing sensitivity analysis, parameter estimations and optimizations and so forth. And this all can be done in a live technical document interface, which is part of the Maple environment. And overall, this really allows you to reduce model development time. And we've had many customers who've told us that before they were using tools like Maple and MapleSim, the kinds of models that they were developing could take months to do, and we're able to produce these the same models with the same fidelity in a matter of days. Okay. Okay, let me just. Okay. So in terms of what we're offering, MapleSim is a part of the, or is integrated with Maple, as I mentioned, so you can switch between the two environments depending on what you want to do. But the important aspect of this particular slide is that once you've created a model, we provide a series of connector tools that allow you to generate code to drop into tools like LabVIEW and MATLAB into Simulink, as Dr. Hashimov's presentation has demonstrated. And the main advantage that we bring to the whole model development world, model-based development world, is the fact that under the hood, we are generating equations. So the models that you create define equations, and they are automatically generated under the hood, which allows us to produce very concise representations of the system models. This can be used for things like analysis within Maple environment, as I mentioned earlier. But because these are very concise representations, we can get the best performance, not only in terms of the simulation within the MapleSim environment, but also from our optimized code generation. So we generate C code of the models that have been developed, which can give us a very significant speed up over similar tools. In the opposite direction, you can use Maple itself to take equations from technical papers or textbooks and enter those equations directly into Maple and then produce custom components in the Maple Sim environment. What this means for the hardware-in-the-loop types of applications is that the code that's being generated is the most optimized that you're going to get. Really, the only way you can get more performance out of the code would be to do this manually. Of course, that takes a lot of time and is error-prone. So we can take the plant model, bring it into the real-time simulation platform, and then connect that up, the model with whatever hardware we want to connect with that. So to wrap up, I think you can see from the presentation that Ajapur has given that physical modeling is increasingly important and is becoming increasingly complex in design of systems, particularly for testing and integration with other subsystems, particularly in robotics and space applications. The use of symbolic technology has proven to be highly effective and significantly improves model fidelity without having to sacrifice real-time performance. And that Maple Sim is an ideal tool for rapid development of high-fidelity physical models of mechatronic systems, robotics, and so forth, to help engineers to achieve their design goals as fast as time possible. So with that, I'd like to thank you for your time, and if there are any questions, we'd be very happy to answer them.
Thank you, Paul and Amir. Very interesting presentation. We'll now open the remaining time for questions. First question, does the software have the capability to create any control code, say in C or C++, from the model?
I can probably answer that. Yes, it does have the capability. We have control design tools. So once you've built the plant model, you can then generate the controller to develop the controller. Now, the only caveat here is that we only generate floating point code. So the target controller has a floating point processor on there. Then we can target that. If you're looking for tools to produce embedded code for fixed point types of applications, then typically the workflow would be develop the plant model in MapleSim and then bring that into a tool like Simulink or MATLAB, and LabVIEW to develop a controller from there.
Okay, thank you. Is it possible to optimize the parameters of any of the models discussed today within MapleSim?
Yes, that's done actually within the Maple environment. So once you've developed the model, you can bring that model into Maple, generate the equations. As I mentioned earlier, all the parameters that are there available to you. You can either assign single values to those parameters, or you can provide constraints to the parameters, and then you can use, we have some optimization tools within the Maple environment, but we also key in quite nicely with some external optimization tools as well.
Okay, thank you. Can you tell me a bit more about the symbolic techniques? How do they simplify and optimize models?
So the primary steps that MapleSim takes is, if we take a look at each of those components that go to make a model in MapleSim, each one of those has mathematical relationships assigned to them, and these can be quite complex relationships. These are further complicated when you start connecting these components together. So our simulation or our modeling environment will take all those relationships and then combine those down into much smaller equations by things like removal of multiplications of ones and zeros, removal of any redundant relationships. It will also take a look at things like common sub-expressions, and particularly in the code generation side, you can take those sub-expressions and pre-assign them to temporary variables. So there are many, many steps that Maple Symbolic simplification tools will be used to get those equations. Now that is just to give you the equations of motion without starting to consider things like model reduction, model reduction techniques, where you can now start making some judgment calls on areas of dynamics that may, for example, you might
tool within MapleSim? If so, what does the MATLAB interface provide?
Sorry, could you repeat that question, please? Could you repeat the question, please?
Yes, sure. Is there a visualization tool within MapleSim? If so, what does the MATLAB interface provide?
Okay, thanks. Yeah, yes, there is a visualization tool. Unfortunately, we weren't able to demonstrate it because the movies didn't work. But all the movies that were that Dr. Hajipur was going to present today, they were all done using our visualization tool. Now, how that fits into the MATLAB Simulink world? Well, there really is no connection. At this stage, all we are doing is taking the code that represents that system model and then dropping that into Simulink as an S function.
I see.
So you can then use the MATLAB's visualization tools to use that, but there's no integration between the two.
I see. Okay. Someone else wants to know if medical device manufacturers are using MapleSim.
I'm aware of it, at least a couple of customers that are doing this. One is a robotics application, which is a surgical application. So the answer is yes. I can't really go into a lot of details because of confidentiality.
I see. All right. That looks like we've gone through the questions that have been posted. And so I'd like to thank everyone for attending this webinar from Design World. This presentation will be emailed to everyone later today and will also be available at designworldonline.com. Thank you all so much.
Many thanks. Goodbye.
Bye-bye.